we shall start some important concept of order of an element in a group. So if you have given a group and you have element, so how to find out the order of an element in the group? So start from the definition. So here the definition is definition. So the definition is, let G be a group with respect to some binary composition, and A be an element of G, and A belongs to G. Then the order of A is defined as, order of A will be n if n is the least positive integer such that a to the power n equals to identity. If there exists no such n exists, so otherwise we say order of A equals to infinity. When if there does not exist any n belongs to natural number such that a to the power n equals to identity. What is E? E is basically the identity element, where E is the identity element in the group. Identity element in G. So now we have an important recall here. So what are the recalls? Let A belongs to G and order of G is finite. Then we must say order of A must divides order of G. So that means order of an element must divide the order of the group. And there is another important result. Let A belongs to G be such that, where G is a group, be such that order of A equals to n. Then we can say order of A to the power k, that will be n by GCD of kn. So this result is very powerful to find out the order of A to the power something. So as for example, you have asked some MCQ type question, like question, let G be a group, let G be a group and A belongs to G, be such that order of A equals to 30, then the order of the element A to the power 18 is, the option A is 1, option B is given 5, option C is 18, and option D is 30. So here just we will use the fact or this important result. So here order of A equals to 30. This is our basically n, and therefore order of A to the power 18, that will be n by GCD of 30 comma 18. So 30 by that is 6, so it will be 5. So option B is correct. All other options are false. Okay, that may be the multiple choice question you have asked in the examination paper. So now we will come to one important concept here. The concept is the conjugate of an element. So here the concept recall is basically conjugate of an element in a group. Conjugate of an element in a group. So what is meant by, what should be the definition here? Let G be a group, G not be a group, and A belongs to G. A belongs to G. So you have given a group G naught and A is an element of G. Then an element B belongs to G is called conjugate of A, is called conjugate of A. If an element B is called conjugate of A, if there exists an element X belongs to G such that B equals to XA X inverse. If this relation holds, then the element B is called conjugate of A. And here the important result is, the important remark or result, if B is, the important remark is, if B is conjugate of an element A in a group G, then order of B must be equals to order of A. So this remark is very much important. So here I will start the question which is given in Calcutta University Math Honours Examination, the year of 2004. So here the question is, in a finite group G naught, show that X and XA X inverse, that means the conjugate element of X, are of same order, for any two elements AX, for any two elements A comma X belongs to G. This question is given for 2 marks. So now here you just try to identify XA X inverse is basically the conjugate element of A. So how will you prove? So here the solution. What is given? G is finite group. So order of G here is finite. So this is less than infinity, where G is a group, finite group, and let, here I am considering let B equals to XA X inverse. So what we have to show? So here we have to prove that, we have to show that the element A and AB are same order. So order of A equals to order of B. Okay. So here what we assume here? We assume here B equals to XA X inverse. So then what will be B to the power some K? So for any K, so then for any K belongs to natural number, B to the power K, that will be XA X inverse whole to the power K. That we can write XA X inverse, XA X inverse, XA X inverse. This is basically K times. And if we apply associativity law, that will be XA X inverse A X inverse X dot X inverse X A X inverse. So this is by associativity property. Associativity. And from that we can write x a to the power k x inverse, since x inverse x equals to identity. This is the identity element in G. Identity element. So what we get? So for any k belongs to natural number, okay, so we get b to the power k equals to x a to the power k x inverse. So from that, what we can write? So therefore, for any k belongs to natural number, we can say a to the power k equals to identity. That implies b to the power k will be identity. And this is also b to the power k identity implies a to the power k. Why? Because if a to the power k equals to e, that implies b to the power k equals to x e x inverse. So that will be x inverse, and that will be e. And that is holds vice versa. So hence if n is the least positive integer, n is the least positive integer such that a to the power n equals to identity, then we can say n is also the least positive integer, the least positive integer such that b to the power n is also identity. So what I conclude? So order of a equals to n. It is if and only if order of b equals to n. So b equals to x inverse. So thus a and x inverse are of same order, are of same order. Okay. So now we come to the next important problem. This will be question number 28. Now we come to the question number 29. So that question is asked in the year of 1999. What was the question? In a group prove that a inverse that will be a where a belongs to G. Okay. So how to solve this kind of question? Let a belongs to G and b equals to a inverse. So then it is obvious b belongs to G. Now we have to show that a inverse equals to a, that is a inverse, that means b inverse equals to a. This is our target. So now what we get? We just calculate AB. So that means A inverse, this is equals to identity. And BA, that means A inverse, this is also identity. So what we get? AB equals to BA equals to identity. And from the definition of inverse, what we can write? B inverse equals to A. Since by the definition of inverse. So what is exactly B? B is our A inverse. So A inverse whole inverse equals to A, since B equals to A inverse. So what we proved? Therefore we proved here in a group G, A inverse whole inverse equals to A for all A belongs to G. Now we come to the next important problem. This is problem number 30. And this question is asked in the year of 2006. What was the question? True or false? Let G be a group and A comma B belongs to G such that B not equals to identity. What is E? E is the identity in the group G. If order of A equals to 3 and AB A inverse equals to B square, then order of B equals to 7. So this is basically a 2 marks question. And okay, we'll see this statement is basically true. So here the solution is the given statement is true. Why this statement is true? We need justification. Without justification, we can't say the statement is true. So we need to justify. So we'll do the justification. What is exactly given? So it is given G is a group and A comma B belongs to G. And it is also given B is not identity. And also it is given order of A equals to 3 and AB A inverse equals to B square. So what we have to show? We have to show that order of B equals to 7. Okay, so now we'll start from it is given AB A inverse equals to B square. And we just squaring on the both side. What will happen? AB A inverse square will be B to the power 4. And that will be AB A inverse. AB A inverse equals to B to the power 4. By associativity, we can write AB A inverse A, B A inverse equals to B to the power 4. So this is by associativity. And that implies AB identity B A inverse equals to B to the power 4. And from that, we can write A B square A inverse equals to B to the power 4. Okay. So now we are trying to increase the power because we need to show B to the power 7 equals to identity at least. So again since B square equals to AB A inverse, so therefore from star what we can write AB A inverse equals to B to the power 4, since B square equals to AB A inverse. And from that we can write a square b a to the power minus 2 equals to b to the power 4. Now since it is given order of a equals to 3, this is given order of a equals to 3, and from that we can write a cube equals to identity, and that is a square equals to the power minus 1, and hence we'll put this is double star, this is triple star. So therefore from double star and triple star, what we can say, a to the power minus 1 b a, that will be b to the power 4, since a inverse that will be a for all a belongs to G, that we have proved earlier. Okay, so that means what we get here, we get here b equals to a b to the power 4 a inverse. Just we pre-multiple by a and post-multiple by a inverse, will get this result. So this is okay. Now from star and now from star and 4 star, what we can, so we can write or we get, b is our a b to the power 4 a inverse. So we can write, okay, from this information, from this we can consider 1, and that we can consider 2. So from 1 and 2, what we get, so b equals to, here we have b square equals to, from 1 we have b square equals to ab a inverse, ab a inverse, and b is basically a b to the power 4 a inverse. Okay, so what we can write, that will be a b to the power 8 a inverse. So AB A inverse, AB A inverse, okay, we get, now from 2, what we get, b square equals to a b to the power 4 a inverse, and b square means a b a inverse, this is by 1, and that we can write a b to the power 8 a inverse. Now we are cancelling both side a and a inverse by cancellation law, b equals to b to the power 8. This is by cancellation law. So that means we get b to the power 7 equals to identity. So b to the power 7 equals to identity, that exactly implies order of b divides 7. And since if a to the power m equals to identity, that implies order of a must divides m. So that means order of b equals to either 1 or 7. Now it is given b not equals to e, and that implies order of b is basically not equals to 1. So order of b must be 7. So we have proved the result. now we come to the next important problem. So this is question number 31, and that question is asked in the year of so the question is in a group G, the element A is of order 2. The element A is of order 2, and for some B belongs to G, we have A B to the power 4A, this is B to the power 7. Show that B to the power 33 equals to E, where E is the identity element in G, where E is the identity element in G. How to solve this problem? So what is given? Given in the group G is an element of order 2, and from that we can write A square equals to identity. And it is also given for some B belongs to G, we have A B to the power 4A, this is equals to B to the power 7. So that we consider as star, and this we consider as 1. So we just squaring both sides. A B to the power 4A square, that will be B to the power 14, and that we can write A B to the power 4A, A B to the power 4A equals to B to the power 14. So by associative law, we can write A B to the power 4 square, B to the power 4A, this is equals to B to the power 14. Now, A square equals to E. So just we will use here, so A B to the power 8A, that will be B to the power 14, since A square equals to identity. So by star. Okay. So what we get? So therefore we get B to the power 14 equals to A B to the power 8A. Now we can write B to the power 8 as A B to the power 7 BA. And since B to the power 7, this is given as A B to the power 4A. So A B to the power 4A. So what we can write? A B to the power 4A BA. So that means we can write it A square B to the power 4A BA. Now since A square equals to identity, that implies B to the power 4A BA. So here we can write B to the power 4, B to the power 14, B to the power 4, B to the power 10, B to the power 4 ABA. Again by left cancellation law, we can cancel B to the power 4 on the both sides. So B to the power 10 equals to ABA by left cancellation law, because the cancellation law holds in a group. So we just raising the power, because we need B to the power 33, we just raising the power. So say B to the power 10 to the power 4 ABA whole to the power 4, and that will be B to the power 40 equals to ABA 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 ABA. So by associative it we can write AB square B square B square BA. So since we know a square equals to identity, if we put here, that will be A B to the power 4A. Okay. So again A B to the power 4A means B to the power 7. So that means what we get here. So therefore that implies B to the power 40. This is equals to B to the power 7. Since A B to the power 4A, this is given as B to the power 7. And that we can write B to the power 7 into B to the power 33, B to the power 7 identity into E. Again we cancel both sides B to the power 7, it will be B to the power 33 equals to the identity element. So we have proved this result. Now we come to some important theoretical question. This is basically question number 32. So the question is, define subgroup. So let G be a group, or you can say let G not be a group, and H be a non-empty subset of G. Non-empty subset of G, then H is called subgroup of G. H is called a subgroup of G if H is a group with respect to same binary composition not. Okay. And here note, we denote it by H is a subgroup of G, that way. So as for example, here if we come to the example, the Z plus set of all integer with respect to addition is a subgroup of set of all rational number with respect to addition. Okay, so now we come to the subgroup test, how we will show our group. So this we come to the important recall. This is called subgroup test. How will test a non-empty set in a group is subgroup or not? What you will do, say let G be a group, then H will be subgroup of G, and H is non-empty subset of G, then H is subgroup of G if and only if A B inverse belongs to H. For all AB in H. or we can say H is a subgroup of G, if and only if AB belongs to H, for all AB belongs to H, and A inverse belongs to H, for all A belongs to H. So this is called the one-step subgroup test, and the next is called the two-step subgroup test. So this is two-step subgroup test, and the previous one is one-step